section 2.7, page 2, and we'll get through the first two examples. So in example 1, we're asked to find dx dt for an equation that consists of x's and y's, and then we're given some values for x, y, and dy dt. So the thing to pick up on is that every variable is differentiated in terms of time. The dy has a dt. The dx has a dt. So we're going to take this equation and differentiate every variable. So y cubed's derivative, and because it was a y, we need to include a dy dt. The minus x squared has a derivative of minus 14x, but because of the x, we need a dx dt. And the 9y has a derivative of 9, but we need to include a dy dt. Now we're trying to solve for dx dt. We could subtract terms over and divide by terms, but instead I think it's easier to just go ahead and plug the values in now. So wherever I see dy dt, I'm going to go ahead and put, and put a negative 4. Wherever I see x, I'm going to head and insert a 2, and wherever I see a y, I'm going to substitute a positive 1. Hopefully the color coordination helped. So 1 squared is just 1 to give me 3 times 1 times negative 4, which is negative 12. This 12 is positive below it for a different reason. I can multiply the negative 14 and 2 to get negative 28, but it's multiplied with dx dt, and 9 times negative 9 times negative 4 is negative 36. Okay, now I'm ready to solve for dx dt. So this is where I will take the opposite of negative 12 in the form of a positive 12 to add to both sides, so that this first term adds to 0, and negative 36 and a positive 12 gives me negative 24. The negative 28 dx dt is on the left, so I'm going to divide both sides by negative 28, and then I'll simplify by dividing both top and bottom of my fraction by 4, and a negative divided by a negative is a positive. So here's another example. Air is being pumped into a spherical balloon so that the volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So the first thing that should jump out at you is you see that how fast is something increasing. I need a derivative. Specifically, I'm going to be finding the derivative of the radius. This is the derivative I want for my answer. Notice I have the derivative of the radius as my answer. And because it says increasing, I'm expecting a positive answer, which I got. Be careful sometimes on the online homework, if it says decreasing, then it's already been implied that it's a negative. So you may not have to enter that into your homework. Okay, so step 1, we were suggested to draw a picture. So here is just a sphere where I can see my radius in the middle. Step 2, figure out all the values and variables you have. Now we're told that the spherical balloon has a volume. So I took the formula for the volume of a sphere, and because it said specifically the volume is increasing, that would be dv dt, the derivative of just the volume. I'm not going to worry about the right side yet because it says the rate that the derivative of the volume is increasing is 100 cubic centimeters per second. So I know that when I get to dv dt, I'm going to plug in 100. Also, when it asks how fast is it increasing, it specifically says when the diameter is 50 centimeters. So we've got a diameter of 50 centimeters, but remember our formula has radius, and we know that the diameter is 2 radii, but I need to find just a single radius. So if I divide both sides, a diameter is 2 radius. If I divide both sides by 2, I've got the r alone, so the radius is half of a diameter. So if the diameter is 50, then the radius is half of that at 25. So I've taken all the information I can from the question, and now I'm ready to go ahead and work. So we said we're taking the volume of a sphere, and I'm going to take the derivative for all of the variables. Remember that just v and r are the variables of this function. Pi is technically a constant. It's always 22/7. And we're taking derivatives about time because the balloon is blowing up over time or being pumped with air. So the derivative of v is dv dt. 4/3 pi is a coefficient, so it stays there. The derivative of r cubed is 3r squared, but I took the derivative of r, so I needed a dr dt. Here the derivative of v was 1, if you needed to think of it that way. So again, instead of solving for dr dt from this original equation, I always think it's so much easier to plug my values in right away. We had decided that dv dt is 100, and we had decided that r is 25. So as I plug all of this in, it catches my eye right away that I have a 3 in a denominator and a 3 in the numerator, so I can go ahead and cancel those. So I'm just left with 4 pi times 25 squared that I'm going to divide to the left side. 4 will go into 125 times. So now I just have this 25 over pi 25 squared. But that means one of the 25's in the numerator can cancel with 1 from the squared term. So in the top of my fraction, I just have a 1. Now I have a single 25 with pi, and that is my numeric value. Don't forget, you need to include units. We're asked about at what rate the radius is changing. So the radius is one-dimensional. So even though the volume of the sphere is cubic centimeters, the radius would just be measured in centimeters. But whenever you have a derivative as an answer, your units are always going to be how is the top measured in centimeters? How is time measured in seconds? I know that because it was measured in seconds in the question. We will solve example 3 on the next video.